Empirical formula is the simplest whole number ratio of the different atoms in a chemical formula. It's always calculated experimentally, so you'll have to follow a series of steps in a calculation to get the answer. The numbers aren't always exactly the whole number, but they should be equating to roughly a whole number ratio. We're going to go through the steps in how to calculate empirical formula using experimental data. So here's an example to illustrate the point. Propene has a molecular formula of C3H6, but the empirical formula of propene is CH2 because the simplest ratio of 3 to 6 is 1 to 2. The empirical formula is CH2 for all the alkenes. This experiment can be used to calculate the molecular formula of magnesium oxide by burning some magnesium in a crucible with a lid. The reason I use a crucible with a lid is because the white magnesium oxide powder is very lightweight and is easily blown away, which can cause experimental errors. We'll try and keep the lid on as much as possible during the experiment to minimise these mass losses. It's important to carry out this experiment on a heat-proof mat because we're dealing with high temperatures. I have a clay pipe triangle which is going to hold the crucible and the lid. It's also important to have tongs available because it's going to get really rather warm. We also have a tripod and a Bunsen burner which we're going to use for heating the apparatus. I've drawn the apparatus here where you can see the crucible sitting inside the clay pipe triangle. The first measurement we need to take is of the empty crucible and lid. I've made sure that the balance is reading 0 before I weigh them. The mass of the empty crucible and lid is 34.46. The next measurement we need to take is of the crucible, lid and the magnesium piece that we're going to react today. That comes out at 34.87. It's important to write both of these values down so we've got them to use later. So now we've made the measurements, we need to heat the magnesium, keeping the lid on the crucible. We're going to heat with a blue flame, and that's going to give the thermal energy to the gas inside, which includes the oxygen, which are going to collide with the magnesium, and the reaction's going to start. When it starts, we should see a bright white light every time we lift the lid until the reaction's finished. We try and keep the lid on as often as possible, only opening the lid to let more air inside. So the oxygen in the air is now moving faster because as we heat substances up, the particles move faster, and the oxygen is more likely to overcome the activation energy when it hits the surface of the magnesium, forming magnesium oxide. Magnesium oxide is a white powder, and we're adding magnesium to oxygen, so the substance we're forming will have a greater mass than the magnesium on its own. This is a combustion reaction because the magnesium is actually burning in air. It's using the oxygen from the air, not all of the air, so some of the gas that's inside there will be nitrogen and other gases, which is why we have to lift the lid periodically. This reaction is an oxidation reaction because magnesium is combining with oxygen to form magnesium oxide. Rapid oxidation is also known as combustion. Inside the crucible, the magnesium may start reacting with the oxygen, but there's not quite enough oxygen to keep the reaction going. So I will have to lift the lid and you may see the fine white powder of magnesium oxide escaping. There's not a lot we can do about that, except keep the lid on as much as possible. Whenever we lift the lid off, we're always going to use the tongs. This experiment is going to get very, very hot. Magnesium burning in air gets to a very high temperature and we don't want to touch it with bare hands. Okay, so we're letting some air in and the magnesium is just starting to burn now. I can lift the lid and I can see the magnesium starting to glow. You may have seen a little bit of white powder there as some of the oxide escapes. There's not a lot we can do about that, but we can put the lid back fairly quickly to make sure we don't lose too much. We're trying to get a complete reaction here, so it may be that I have to prod the magnesium or shake the crucible just to make sure all the metal has reacted. Of course, if I prod too hard, I could damage the apparatus, or I could end up with magnesium oxide on the end of the tongs, which will subtract some of the mass as well, giving me further errors. We just have to look at the experiment and see how we're progressing. This is burning really well because we've got it nice and hot, and the air is now getting into the crucible, and I can see all of the magnesium ribbon burning. It's a bright white light, and the magnesium metal is turning white. I can see some of the white powder escaping there, so I'm putting the lid back on. Just going to lift the lid again to see if the reaction is going to continue. It is, because as soon as I lifted the lid and new air entered the crucible, it started to glow again and the fire started up inside. So it is glowing. I'm going to put the lid back on because we're getting some powder formed. The reaction is quite vigorous and can throw some of the powder into the air, which gets taken up by the air moving past the crucible. Put the lid back on and let the reaction continue and use the oxygen from the air that's already trapped inside. Using the law of conservation of matter, where no atoms are created or destroyed, the reason the magnesium is getting heavier is because we're adding oxygen to the magnesium. We're bonding oxygen onto magnesium to form the magnesium oxide. We therefore expect the mass to increase. The way I can calculate the increase in mass is by subtracting the empty crucible and lid from the mass of magnesium oxide in the container. What's left over is just the mass of the magnesium oxide. I can do the same with the magnesium by subtracting the empty crucible and lid from the mass of the empty crucible and lid with the magnesium inside it. I can work out how much magnesium I had. I can work out how much oxygen was added to the magnesium by subtracting the magnesium from the magnesium oxide. The mass remaining is the oxygen. It's been about 10 minutes now, and we can tell the reaction has finished because when I lift the lid, there's no more glowing and no more flame. It just looks like white ashes at the bottom of the crucible. Even when it's disturbed, there's no more reaction. So now it's sensible to turn off the Bunsen burner and let the apparatus cool completely. It's been half an hour now, and we have a cold crucible of magnesium oxide. The next measurement we need to make is the crucible with the magnesium oxide in it. So let's take the mass of the magnesium oxide in the crucible. The mass comes out to be 35.12 grams. Let's record that in the table and do the calculation. So here are the three values from our experiment. We have the empty crucible and lid, we have the magnesium inside the crucible with its lid on, and we have the crucible with its lid filled with magnesium oxide. To get the mass of magnesium, I subtract the empty crucible and lid from the crucible, lid and magnesium value. Here. I end up with a value of 0.41 grams of magnesium. I can calculate the amount of oxygen that has added itself or bonded with the magnesium by subtracting the magnesium inside the crucible and lid from the magnesium oxide crucible and lid value. Here. I get a value of 0.25 grams. We're going to take these data values forward and calculate the formula. The first step in our calculation is to write the elements in their columns and put the masses underneath. In the second step, you divide both sides by their respective relative atomic masses, taken from the periodic table. The third step is to take both answers and divide by the smallest value. That gives us a ratio. The ratio tells us what the formula is. In this case, the ratio comes out to be 1 to 1, because if you remember, the empirical formula is the nearest whole number value that we're going to take. These are always calculated experimentally, and you can see from real-life data that they don't always end up as exact numbers. Your job is to take those exact numbers from the answer. The third step in my calculation is to divide the answer by the smallest of the answers I've got. That gives me a ratio. Now the data is not perfect because they're using experimental values. This gives me a ratio of 1 to 1 using the nearest whole number. My answer, therefore, for the formula of magnesium oxide is Mg1O1 or MgO. So let's walk through the calculation one more time. Using the values which we measured from the experiment, we put them into two columns for each element. We then divide the numbers by the relative atomic masses of each element, taking those values from the mass numbers of the periodic table. The next step is to divide through by the smallest value. That gives us a ratio. Remember, empirical formula is the simplest whole number ratio, so we take them to roughly the nearest whole number, assuming that they're approximately near a whole number, and that gives us the final answer for the formula. So that's the simplest whole number of the elements in a compound. Empirical formula's finished. Click the link or scan the code and be taken to your notes.